Morning breaks across the Caribbean with turquoise water stretching to every horizon, fishing boats departing quiet harbors, cruise ships tracing familiar routes, and millions of people beginning another ordinary day on islands celebrated for their beauty. From Puerto Rico to the Dominican Republic and the Virgin Islands, life appears inseparable from the sea. Yet far beyond the beaches and coral reefs lies a place so immense, so remote, and so little understood that it has become one of the Atlantic Ocean's greatest geological mysteries. Hidden beneath thousands of feet of seawater, a narrow scar carved into Earth's crust descends farther than any other location in the Atlantic. Scientists know it as the Puerto Rico Trench, and within its deepest depression rests Milwaukee Deep, a place where darkness, crushing pressure, and relentless tectonic forces combine in remarkable fashion. It is not merely the deepest point in the Atlantic Ocean. It also occupies one of the planet's most complicated and potentially hazardous plate boundaries, where powerful geological forces continue shaping the Caribbean region even during long periods of apparent silence. Unlike many of the world's famous ocean trenches, the Puerto Rico Trench does not fit neatly into a single geological category. Many trenches form where one tectonic plate steadily dives beneath another in a relatively straightforward process called subduction. The Puerto Rico Trench tells a more complicated tale. Here, several forms of plate motion occur simultaneously. Compression, sideways movement, stretching and bending all influence the landscape beneath the sea. The result is an extraordinarily complex fault system, capable of producing destructive earthquakes, seabed deformation, underwater landslides, and, under the right circumstances, tsunamis that can travel across entire ocean basins. Milwaukee Deep marks the lowest known point within this enormous trench, reaching a depth of approximately 27,500 feet, or about 8,380 meters. At such depths, the pressure exceeds 800 times that experienced at sea level. Sunlight never penetrates this abyss. Temperatures remain only a few degrees above freezing, while the immense weight of the ocean presses relentlessly upon every exposed surface. Even with modern technology, reaching Milwaukee Deep remains a significant scientific achievement, requiring highly specialized deep-diving vehicles capable of surviving one of Earth's harshest environments. Despite its intimidating depth, Milwaukee Deep is only one feature within a much larger geological system extending for nearly 1,000 miles, or roughly 1,600 kilometers, eastward from the Dominican Republic and Puerto Rico toward the northern Lesser Antilles. The trench outlines a major boundary separating the North American plate from the Caribbean plate, two enormous slabs of Earth's lithosphere that have interacted for tens of millions of years. Their movement has created mountain ranges, volcanic arcs, deep ocean basins, and an intricate network of faults stretching beneath both land and sea. Understanding why this region deserves close attention begins with recognizing that tectonic plates rarely move in simple directions. Earth behaves less like a collection of rigid puzzle pieces, and more like an interconnected shell, whose enormous fragments respond differently depending on their location. Along some boundaries, plates collide head-on. Elsewhere, they slide past each other horizontally. In other places, they pull apart. Around Puerto Rico, several of these motions occur together, creating one of the world's most mechanically complicated plate boundaries. The North American plate slowly moves generally toward the west-southwest relative to the Caribbean plate. That movement averages only about 3/4 of an inch to roughly 1 inch each year, or approximately 2 to 3 centimeters annually. Such motion seems insignificant over the course of a human lifetime. Yet geological time transforms those tiny annual movements into tremendous forces. Rocks do not slide smoothly forever. Instead, friction locks portions of the boundary together. Stress accumulates year after year, decade after decade, sometimes for centuries, until the rocks can no longer resist the pressure. When they finally rupture, the stored energy radiates outward as seismic waves, producing earthquakes capable of shaking entire regions. Adding further complexity, not every portion of the boundary behaves identically. Some sections experience partial subduction, where the North American plate bends downward beneath the Caribbean plate. Nearby segments accommodate more sideways motion along strike-slip faults. Other areas undergo extension, where crustal blocks stretch and fracture. These overlapping mechanisms produce an ever-changing mosaic of stresses that challenge even the most advanced geological models. Scientists have spent decades mapping the seafloor surrounding Puerto Rico using multi-beam sonar, seismic reflection surveys, satellite measurements, and deep-sea exploration vehicles. Every expedition has revealed additional evidence that the trench contains far more than a simple groove carved into the ocean floor. Towering underwater cliffs rise thousands of feet above adjacent basins. Massive fault scarps slice across sediment-covered slopes. Ancient landslide deposits spread across wide areas, suggesting that portions of the seafloor have collapsed catastrophically in the distant past. Each discovery reinforces the conclusion that the region remains tectonically active despite extended intervals without truly catastrophic earthquakes. For generations, many people imagined the Atlantic Ocean as relatively quiet compared with the Pacific's famous Ring of Fire. While the Atlantic certainly experiences fewer major subduction zones, the Puerto Rico Trench stands as a notable exception. It represents one of the Atlantic's most active tectonic environments, combining deep earthquakes, shallow earthquakes, crustal deformation, and submarine faulting within a relatively compact region surrounded by densely populated islands. Puerto Rico itself illustrates the close relationship between geology and everyday life. Mountain ranges crossing the island reveal millions of years of tectonic uplift, while coastal plains preserve evidence of repeated changes in sea level and earthquake activity. Offshore, numerous faults continue accommodating plate motion beneath waters that appear calm from the surface. Residents may experience months or even years, with only occasional minor tremors before clusters of earthquakes remind everyone that enormous geological forces remain continuously at work. Historical records reveal that the Caribbean has experienced destructive earthquakes since long before modern instruments existed. Early Spanish colonial accounts describe violent shaking that damaged settlements, churches, forts, and harbors. While construction methods often contributed to the destruction, many reports clearly document intense seismic activity capable of altering coastlines and triggering landslides. These written observations, combined with geological evidence preserved in sediments and uplifted shorelines, allow researchers to reconstruct centuries of seismic behavior across the northeastern Caribbean. Among the most significant events occurred during the early 20th century, when a powerful earthquake struck northwest of Puerto Rico. The earthquake generated strong shaking across much of the island, damaging buildings, cracking roads, and frightening residents who rushed into open spaces seeking safety. More importantly, it generated a tsunami that reached coastal communities within minutes. Several waves swept ashore, flooding low-lying areas and claiming lives before organized warnings could be issued. The event demonstrated that even earthquakes occurring offshore can rapidly become deadly through the combined effects of shaking and rising water. Modern analyses indicate that the tsunami resulted not only from fault movement, but likely from submarine landslides triggered by the earthquake itself. This distinction carries enormous importance because underwater landslides can displace large volumes of seawater, even when the earthquake producing them is only moderate in size. Around the steep slopes bordering the Puerto Rico Trench, sediments accumulated over thousands of years may become unstable during strong shaking. When these materials collapse downslope, they can amplify tsunami generation beyond what fault displacement alone might produce. Evidence of ancient submarine landslides extends across broad sections of the trench system. High-resolution mapping has identified enormous debris fields scattered along the seafloor, some covering areas comparable to major metropolitan regions. These deposits testify that underwater slope failures have occurred repeatedly throughout geological history. Determining exactly when they formed remains difficult, yet their existence confirms that gravity, tectonic stress, and unstable sediments continue interacting beneath the Caribbean Sea. Researchers also recognize another important characteristic of the Puerto Rico Trench. Long periods of relative quiet do not necessarily indicate that tectonic hazards have disappeared. Earthquake occurrence often follows irregular patterns rather than predictable schedules. Some faults release stress gradually through numerous smaller earthquakes, while others remain locked for generations before rupturing in larger events. Distinguishing between these behaviors requires constant monitoring, sophisticated modeling, and continuous refinement of geological understanding. This uncertainty often creates a false sense of security among populations living near active faults. Decades without a devastating earthquake can lead communities to believe the danger has diminished. In reality, the physical processes responsible for future earthquakes continue operating regardless of whether humans notice them. Plates continue moving. Rocks continue deforming. Stress continues accumulating. The absence of disaster merely reflects that the necessary conditions for rupture have not yet reached their critical threshold. Milwaukee Deep, therefore, represents far more than an impressive geographic record. It serves as the deepest visible expression of a tectonic boundary whose influence extends across the entire northeastern Caribbean. Every earthquake recorded near Puerto Rico, every subtle movement detected by satellite positioning systems, every newly mapped fault beneath the ocean, and every sediment core recovered from the seafloor contributes another piece to an immense geological puzzle that scientists are still striving to assemble. As research vessels continue exploring this remarkable trench, each discovery strengthens the understanding that the Atlantic Ocean's deepest abyss occupies a fault zone whose quiet intervals should never be mistaken for permanent calm. Silence can be one of the most deceptive characteristics of an active fault system. Across the northeastern Caribbean, months may pass with only minor tremors that barely register beyond local communities. Years may unfold without a single destructive earthquake. The sea remains calm, shipping lanes remain busy, and coastal cities continue expanding toward the shoreline. Yet every passing day represents another interval during which tectonic forces continue reshaping the region at a pace too slow for human senses to perceive. Deep beneath the Atlantic, the North American plate continues pressing against the Caribbean plate, and the immense stresses generated by that movement never truly disappear. Unlike a classic subduction zone, such as those surrounding much of the Pacific Ocean, the Puerto Rico Trench occupies what geologists describe as an oblique plate boundary. Instead of moving directly toward one another, the plates converge at an angle. This seemingly subtle difference changes nearly everything about the mechanics of deformation. Part of the motion drives one plate downward, while another portion is accommodated through horizontal sliding along strike-slip faults. Additional stress may be released through stretching and normal faulting in nearby regions. Rather than concentrating energy along a single fault plane, deformation becomes distributed across an extensive network of interconnected structures beneath both the ocean floor and the surrounding islands. This complicated arrangement explains why earthquakes occur throughout the region at a wide range of depths. Some originate only a few miles beneath the seafloor or several kilometers below the ocean bottom, where brittle rocks suddenly fracture after years of accumulated stress. Others occur much deeper within the descending North American plate as it bends and sinks into Earth's mantle. These deeper earthquakes may be felt across large areas because seismic waves travel efficiently through the cold, dense rock of the subducting slab. Although they are less likely to produce destructive tsunamis than shallow offshore earthquakes, they provide important evidence that plate movement continues far below the surface. Scientists studying seismic records have identified a broad zone of earthquakes extending downward from the trench into Earth's interior. This inclined band of seismic activity outlines the path of the descending plate and reveals that the North American plate does not simply slide beneath the Caribbean plate in a smooth, uninterrupted fashion. Instead, it bends, fractures, and deforms while descending, producing earthquakes over a remarkable range of depths. Every earthquake contributes valuable information, allowing researchers to refine their understanding of the hidden geometry beneath the Caribbean. The Puerto Rico Trench itself also displays dramatic differences along its length. Certain segments exhibit characteristics associated with stronger compressional forces, while neighboring sections reveal more evidence of sideways movement. Some portions contain steep escarpments rising thousands of feet from the trench floor. Others display complex terraces, sediment-filled basins, and fault-controlled ridges. These variations reflect differences in rock composition, fault orientation, sediment thickness, and the history of plate interactions accumulated over millions of years. One of the greatest challenges facing geologists is determining which faults currently store the greatest amount of elastic strain. Modern satellite positioning systems can detect movements measured in fractions of an inch, or mere millimeters, allowing scientists to observe how islands slowly shift relative to one another over time. Networks of continuously operating global positioning system receivers scattered across Puerto Rico, the Virgin Islands, Hispaniola, and neighboring islands reveal that the crust is constantly deforming. Although these measurements appear almost insignificant on a daily basis, they demonstrate that plate motion remains active and measurable. The data show that different parts of the region move at slightly different rates and in different directions. Such variations indicate that stress is not distributed evenly. Instead, certain faults may be locked by friction, while adjacent structures creep gradually without generating major earthquakes. Locked faults accumulate strain much like a compressed spring. As stress increases beyond the strength of the surrounding rocks, rupture eventually occurs, releasing decades or centuries of stored energy within seconds. Marine geophysicists complement satellite observations with detailed mapping of the ocean floor. Multi-beam sonar systems emit sound pulses toward the seabed and measure the returning echoes, producing highly detailed topographic maps. These surveys have transformed scientific understanding of the Puerto Rico Trench. Features once believed to be relatively smooth are now recognized as landscapes filled with towering cliffs, fractured ridges, deep canyons, and enormous fault scarps. Some underwater escarpments rise several thousand feet, or well over 1,000 meters, creating relief comparable to major mountain ranges, despite remaining permanently hidden beneath the sea. Sediment cores extracted from the trench provide another valuable archive. Layer after layer of mud, volcanic ash, microscopic marine organisms, and mineral grains accumulate slowly over thousands of years. Disturbances within these layers often record ancient earthquakes and submarine landslides. Thick deposits of chaotic sediment may represent moments when powerful shaking destabilized underwater slopes, sending vast quantities of material cascading into deeper basins. By dating these deposits, scientists reconstruct a long-term record of geological activity extending far beyond written history. The possibility of submarine landslides remains one of the most significant hazards associated with the Puerto Rico Trench. Along the steep margins of the trench, thick accumulations of sediment rest on inclined slopes already weakened by countless fractures. During strong earthquakes, these sediments may lose stability and fail almost instantly. Entire sections of the seafloor can collapse, accelerating downslope at remarkable speeds while displacing enormous volumes of seawater. Unlike tsunamis generated solely by vertical fault displacement, landslide-generated waves often develop rapidly and may direct their greatest energy toward nearby coastlines. Communities closest to the source therefore face exceptionally short warning times. Depending on the location of the failure, waves may reach nearby shores within only several minutes, leaving little opportunity for official alerts before inundation begins. This reality underscores why earthquake preparedness remains just as important as tsunami warning systems throughout the northeastern Caribbean. Another characteristic distinguishing the Puerto Rico Trench from many better-known subduction zones is the absence of a continuous chain of active volcanoes directly above the trench. In regions such as the Western Pacific, subduction commonly produces extensive volcanic arcs, as water released from the descending plate promotes melting within the overlying mantle. Around Puerto Rico, the geological setting differs substantially. The geometry of the subducting slab, the age and composition of the oceanic crust, and the evolving history of Caribbean plate motion have created conditions in which significant volcanism is largely absent immediately adjacent to the trench. This absence sometimes leads to misconceptions about regional hazards. Without dramatic volcanic eruptions, people may underestimate the tectonic activity occurring below the surface. Yet earthquakes require no erupting volcano to become destructive. Massive strike-slip faults, thrust faults, and normal faults all possess the capacity to release tremendous amounts of stored energy independently of volcanic activity. The Puerto Rico Trench illustrates this principle clearly, demonstrating that seismic hazards remain substantial even where volcanic hazards are comparatively limited. Historical records combined with modern seismic catalogs reveal that earthquakes frequently occur throughout the northeastern Caribbean. Most remain too small to cause widespread damage, serving instead as reminders that stress continues adjusting within the crust. Occasionally, however, larger earthquakes occur in clusters, reflecting the transfer of stress from one fault segment to another. After one rupture releases energy, neighboring faults may experience increased stress, altering the probability of additional earthquakes over periods ranging from days to many years. Scientists continue refining computer models capable of simulating these interactions, although predicting the precise timing of future earthquakes remains beyond current scientific capability. Researchers can identify faults capable of generating damaging earthquakes, estimate their maximum potential magnitudes, and evaluate the likelihood of future activity over extended periods. They cannot determine the exact day or hour when accumulated stress will exceed the strength of the rocks. This uncertainty makes preparedness an essential component of life throughout tectonically active regions. The waters surrounding Puerto Rico, Hispaniola, and the Virgin Islands also contain thousands of miles of critical infrastructure. Fiber optic communication cables crossing the Atlantic carry enormous quantities of global internet traffic. Commercial shipping routes connect ports throughout North America, South America, Europe, and the Caribbean. Energy facilities, tourism, fisheries, and coastal industries all depend upon reliable marine transportation. A major submarine earthquake or landslide therefore possesses consequences extending far beyond the immediate coastline. Damage to underwater cables, port facilities, and maritime infrastructure could disrupt communications and commerce across a much wider region. Advances in deep-sea exploration have begun revealing details once considered impossible to observe. Autonomous underwater vehicles glide only a short distance above the trench floor, collecting remarkably detailed imagery of fractured rock formations, sediment deposits, and fault scarps. Remotely operated vehicles equipped with cameras and sampling equipment investigate locations that remain inaccessible to conventional research methods. Pressure-resistant instruments placed on the seafloor continuously monitor seismic activity, water pressure, and subtle crustal deformation. Together, these technologies transform the trench from an inaccessible abyss into a closely studied natural laboratory.